to this workshop over writing and balancing chemical equations and predicting the products of chemical equations. Now, first of all, I'd like to go over the different types of chemical reactions. So there's 5 basic types of reactions. Types of reactions. And you can tell what the reaction is based on just looking at its reactants. So, for example, the first type of reaction is what I call synthesis or combination. Synthesis, or sometimes called combination. And a synthesis reaction or combination reactions is essentially when 2 or more elements or compounds combine to form a single product. And so there's a general formula, a general pattern here. Usually it's, A plus B goes to form C, okay, which is the combination of the two. Okay. 2 or more reactants combine to form a single product. It's the fact that it forms a single product that is the obvious giveaway in synthesis. But if a product is not given, if each of the reactants are elements, you can know for certain that it is going to be a synthesis. Okay. So, an example of this would be if I have H2 plus Cl2. Okay. Well, H is, they're both elements. In this case, they're both diatomic. But when you put them together, you'll put them together according to their charge. Hydrogen tends to have a +1 charge. Chlorine tends to have a -1 charge. So this will be HCl. Okay. So when you're predicting the products, make sure that you do not worry about the subscripts over on the other side, because those may change. Focus on the charges given. In this case, it's in +1 and -1 for hydrogen and chlorine, and so those are balanced, so it'd just be this. Alternatively, if you have something like this, you have aluminum and oxygen in a synthesis or combination reaction, the charge of aluminum, well, aluminum is a metal, right? And oxygen is a non-metal. So when a metal combines with a non-metal, what type of compound does that form? Ionic or covalent? When a metal combines with a non-metal, what type of compound does that form?
Ionic.
Ionic. So what's the charge of aluminum in an ionic compound?
+1.
3+ actually, right?
Just kidding, I thought it was silver.
And what's the charge of oxygen in an ionic compound?
-2.
-2. So if oxygen's a 2- and aluminum's a 3+, what's the formula for aluminum oxide of the product? Sorry?
Al2O3.
Al2O3. Al2O3. Because see, the lowest common multiple of 3 and 2 is 6, right?
Yes.
And so you can think of it like this. If I have aluminum with a 3+ charge and chlorine, or I'm not chlorine, sorry, oxygen with a 2- charge, the multiples of 3 would be 3, 6, 9, 12. Multiples of 2 are 2, 4, 6, 8. So if you look for the lowest common multiple, it's going to be the 6, right? It's the lowest multiple they both have in common. And that means you need 2 aluminums to get a charge of 6 and 3 oxygens to get a charge of 6. Does that make sense?
Yes. It's gonna help.
All right, so that's synthesis reactions. So now let's look at its evil twin, shall we say, decomposition. So decomposition reactions are effectively the exact opposite of synthesis reactions. A decomposition reaction is when one reactant breaks apart into multiple products. Okay, so usually the most common type of decomposition reaction is when a compound breaks up into its component elements. So unstable ionic compounds such as, oh, by the way, yes, the general formula or the general form for this type of reaction would be the opposite of synthesis. So C breaks up into A plus B. Although it is possible that one reactant could break up into more than 2 products. It could break up into 3 or 4. But whenever there's only one reactant, you know that it's a decomposition reaction. And typically, it breaks up into its elements. Now, and a good example of this would be, like say for example, an unstable oxide, such as silver oxide. So if you have Ag2O, if you heat silver oxide up, it's pretty unstable. It actually will break apart into silver metal and oxygen gas. And actually, that means I have to rebalance this. 2, 4, and 1. Silver metal and oxygen gas. Now you may wonder why I chose to make this O2 instead of just putting it as oxygen. Well, it turns out that there are several elements on the periodic table that do not exist as single atoms. They're just too unstable. They will not form single atoms. Instead, well, at least not under normal circumstances. Instead, you will find them always as diatomics. And so those 7 elements really, excuse me. I'm going to go ahead and erase this, is that okay? Okay. So the 7 elements that form diatomic molecules, that's the only way they exist in nature, or at least the most common way they exist in nature, are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. If you look on your periodic table, your general periodic table, okay, it actually makes kind of a little L. So upside down L, so you have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And then there's also hydrogen, which is also included. But yeah, or you can remember the little acronym Brinkelhoff. So that's also helpful. So just keep that in mind whenever you're writing these equations. If it gives you physical descriptions, you're going to want to make sure that those descriptions are translated into the right things. Whenever it says reacts with oxygen, or reacts with chlorine, or reacts with bromine, you'll put O2, Br2, or N2. or CO2. And last but not least, sorry. There you go. All right. So continuing on, let's look at some other types of reactions, and then we'll work on doing some practice with predicting the products and balancing. Okay, so the next type of reaction is single replacement. So the single replacement reactions are a type of redox reaction, generally speaking. What happens is, in a single replacement reaction, an element and a compound, usually an ionic compound, but not always. An element and a compound react to form a new element and a new compound. So, the general form of this is basically A reacts with BC to form AC plus B. And this is, of course, if the element is a metal. If A is a metal, or hydrogen, really. Because hydrogen is positively charged, so it'll swap places. Or you could also have A plus BC goes to form BA and C, and that would be if A is a nonmetal. Because nonmetals tend to form negative charges. Okay. Now, the basic principle of predicting these types of reactions is that like replaces like. So like replaces like. So if you have a positive charge, it will switch places with the other positive charge. Okay? If you have a negative charge, it will switch places with another negative charge. Alright. So now, let's go ahead and do the double replacement reaction. So you have the double replacement. And double replacement is actually pretty similar to single replacement, except with the double replacement, which is sometimes called a metathesis reaction. You may have heard that term in lab. Double replacement reactions, otherwise known as metathesis or exchange. That's what metathesis means, exchange reaction. This is a reaction where two compounds switch ions. To form two new compounds. Okay. So, in this case, the general form would be like AB plus CD goes to form AD and CB. Once again, like replaces like. Positive charges will switch places with positive charges. And that's what you notice here. The A switched places with C, so that the A is now with the D and the C is now with the B. And an example of this type of problem would be like AgNO3 plus goes to form AgCl plus sodium nitrate. So one thing to kind of keep in mind here, the charge on silver here is +1, charge on nitrate is a -1, charge on sodium is a +1, charge on chlorine is a -1. When they switch places, you put them back together according to their charges. In this case, the charges are the same. The charges are +1, -1, +1, and -1. So when you put them back together, you put them back together in a 1-to-1 ratio. But if the charges are not the same, then you have to put them back together according to their charges. And we're going to do some examples like that. Also notice that positive charges do not go together, right? Like charges repel, opposite charges attract. So you're going to put this positive charge with the chlorine. And kind of a goofy analogy, kind of works, it helps you remember. You can think of this as kind of like relationship drama from back in high school, okay? This couple breaks apart, and this is the guy. See, this couple break apart, he likes the girl, so he's going to start dating the girl, and the other guy's going to be off by himself. Or in here, you have two couples, and they switch places. Now, when the couples break apart, the two guys don't start dating each other, right? It's the guy with the other girl and the girl with the other guy, right? It's a little goofy analogy, but it does kind of stick with you and it'll help you remember that when you're switching these ions, make sure that the ions switch places with ions that, and so that it goes with opposite charged ion. Now, we're going to go to the last type of predicting products, the last type of reaction. Oh, sure, go ahead. It's the last type of reaction, and it is the easiest to predict because the products are always the same. And the last major type of reaction you have to keep in mind, and that is combustion. Combustion. So, in a combustion reaction, excuse me. So in a combustion reaction, a hydrocarbon now, hydrocarbons usually in the form of CXHY. The number of hydrogens and the number of carbons can be different. You can have C4H10 or C4H8. It depends on the structure of the compound and the number of double bonds, but essentially the pattern is the same, CXHY, some sort of hydrocarbon. Now, you can also have a hydrocarbon with oxygen. It could be CXHYOZ. But mostly these combustion reactions that you're going to see are just going to be a plain hydrocarbon with oxygen. So a hydrocarbon reacts with oxygen. Oxygen. To form the same two products every time. To form CO2, carbon dioxide, and H2O. So a hydrocarbon reacts with oxygen to form CO2 and H2O. So the nice thing about this is that it's really easy to see if it's a combustion reaction, because if you see anything with the general formula of CXHY and it's reacting with oxygen, you know you have a combustion reaction and the products are going to be carbon dioxide and water. Sorry. So, there you go. Those are the 5 basic types of reactions. Synthesis, decomposition, single replacement, double replacement, and combustion. So now, let's go ahead and look at writing chemical equations when we're given a reaction description. So the first one, so if you pull up this page I've handed out to you. Okay, so you look for keywords, of course. Usually reactants are listed first, but it'll say something and something go to form or make something else, or it'll say something is produced from something and something else. So identify the reactants and the products. In this case, let's take a look at the first one. So aluminum and oxygen make aluminum oxide. So aluminum is just going to be aluminum metal. Oxygen would be what? O2. Remember the Brinkelhoff, it has to be diatomic. So that's going to form aluminum oxide. Now in this case, aluminum is a metal, oxygen is a non-metal, so that's going to form what type of compound? Ionic. And since it's ionic, we're going to look at the charges. What would the charge of aluminum be? 3. And the charge of oxygen?
2 minus 2.
Minus 2. So I think we actually already did this one as an example, but we get aluminum oxide. Now when we're trying to balance this equation, one of the easiest ways to balance, though it's a little time consuming, is to list out the elements and how much of each you have. So I have aluminum and I have oxygen on this side, and I have aluminum and I have oxygen on this side. If you have elements on one side that are not on the other, you have a problem. So you should have the same elements on both sides. And ideally, I would encourage you to write them in the same order as well. It keeps better track of them. So on this side, how many aluminums do we have?
1.
1. On this side?
2.
And on this side, how many oxygens?
2.
And on this side?
3.
Okay. So now if we wanted to, we could balance the aluminums pretty easily. Keep in mind that coefficients are multipliers. They multiply the element in front of them. So if there's 2 aluminums here, and I want to make this the same, what do I have to do? Go to 2, right? 2 times 1 is 2. But now I have a little problem. I have 2 oxygens on one side and 3 on the other. Whenever you have an odd number on one side that you're trying to balance with an even number on the other side, double the odd to make it even and then rebalance. Double the odd to make it even and then rebalance.
So, can you say that one more time?
What?
When you want to, I want to write it down. Oh, you just said now.
Oh, yeah. Whenever you have an odd number of atoms on one side that you're trying to balance with an even number of atoms on the other side, double the odd to make it even and then rebalance. So, which one of these has an odd number of oxygens? Yeah, the right side. So I doubled that by doubling the coefficient. Right now the coefficient is 1, I'm going to change it to a 2. That's going to multiply, remember it's a multiplier, it's going to multiply the aluminum and the oxygen. So I now have how many oxygens?
You have 6 oxygens and 4 aluminum.
Yeah, I have 6 oxygens and 4 aluminums. So, now that I have that, now I can rebalance everything else. So, since I unbalanced aluminum, I'm going to have to rebalance it. What am I going to have to put in front of the aluminum? 4, yeah. And what am I going to have to put in front of the oxygen?
3.
3. 3 times 2 is 6, right? It's a multiplier. So, there you go. 4, 3, and 2 are the coefficients. Not too bad, right? Let's try one that's a little bit more challenging. Oh, by the way, what type of reaction was this?
First one,
The first one?
synthesis.
Synthesis, combination. Synthesis or combination reaction. There's only one product, so this is a synthesis reaction. If you weren't given this, how could you tell which one it is? By the fact that it was only one element and another element. When two elements are reacting, the only thing they can really do is combine, right? So that's combination or synthesis. All right, let's look at another one. I want to find one that's new. Relatively new. Okay, let's try. Why not? Let's do number 2. It says sodium hydroxide and hydrogen sulfate produce sodium sulfate and hydrogen hydroxide. Well, what's sodium hydroxide?
NaOH.
NaOH. Now, if you didn't know that offhand, you could say, well, sodium is a +1 charge, and hydroxide is a -1 charge. So, and of course, this means that you actually kind of have to memorize those polyatomic ions, which you were kind of supposed to memorize a while ago. But yeah, if the charges are equal, it's just going to be one of each. So sodium hydroxide there, and then hydrogen sulfate. What's the formula for hydrogen sulfate?
HSO4, H2SO4.
H2SO4, which is also called sulfuric acid. Now, why the 2?
Because SO4 has a -2 charge.
There's a -2, and hydrogen has a
+1.
+1. Since hydrogen's a +1 charge, and sulfate's a -2 charge, it would have to be H2SO4. Because you remember, you have to balance the charges in any compound that's ionic or acidic, an acid or an ionic compound. The positive charges have to be equal to the negative charges. Since there's +1 for hydrogen, I have two hydrogens to balance with the -2 sulfate. All right, so now we're going to put our products out. Now the products are going to be what? It tells us it's sodium sulfate, right? What's the formula for sodium sulfate?
Na2SO4.
Na2SO4. Once again, +1 for the sodium, sulfate's a -2. So, if you learn the crisscross method, you can use the crisscross method. I don't like it, but you can. Just keep in mind that when you use the crisscross method, if this is a -2 and this is a +1, keep that parentheses around that polyatomic ion until you're done crisscrossing, because the 2 will come down here, but this is a 1, that's going to come down here. But don't replace that 4 with a 1. That just means you have 1 sulfate, okay? Afterwards, if you only have 1 polyatomic ion, you can take off the parentheses. But just be careful with that, because that's a very common mistake that I see a lot of students make when they use the crisscross method, okay? All right, now, sodium sulfate, and then hydrogen hydroxide, which is just
HOH.
HOH. And another name for that is called water. H2O. Dihydrogen monoxide. Hydrogen hydroxide. Water. Deadly in large quantities. Alright, so now all you have to do is balance it. This can be a little bit intimidating, but if you list out your elements, not so bad. So I have, on my element side, I have sodium, Na, I have O, I have H, and I have S. Okay? I'm going to list the same elements over here, Na, O, H, and S. Now, there are some people who will tell you to keep the polyatomic ions together. I am not one of those. And the reason that I discourage that is 2 reasons. One, sometimes polyatomic ions do break apart. Okay? And 2, it doesn't really make it any easier. So, there's not really that much point in keeping the polyatomic ions together. But how many sodiums do you have here?
One.
One,
1. And oxygen?
5,
5. Make sure that you're counting from both of them. Hydrogens on this side.
3,
3. 2 plus 1. And sulfurs?
1,
1. How many sodiums on this side?
2,
2. Oxygens?
5,
Hydrogens?
2,
And sulfurs?
1.
Okay. Now, in a case like this, where it's a little bit more complicated, what you want to make sure that you do is balance whatever is easiest to balance first. And the easiest elements to balance are those that appear in the fewest places. So for example, how many compounds, how many substances, each one of these is a place or a compound. How many compounds does sodium appear in the entire equation?
1. And
2, right?
6.
It has to appear in 2 places, right? At least once on the product and one on the reactant side. 2 is the minimum number. Okay, so sodium appears in 2 places. What about oxygen?
4,
4 different compounds oxygen appears in. Hydrogen?
3,
3. And sulfur?
2,
2. So sodium appears in twice, oxygen in 4 different compounds, hydrogen 3, sulfur 1. Or sulfur 2, sorry. So what we need to do, what we want to do, is balance whatever is easiest to balance, those that appear only in 2 places, right? Ones that appear in the fewest places are going to be the easiest ones to balance. So I have 2 sodiums here and I have 1 here, so what do I want to do?
put a 2 in front of the
Precisely. So I put a 2 in front of NaOH, and then that's going to change my values. I'm now going to have 2 sodiums. It also changes my oxygens. How many do I have now?
6,
6. 2 times 1 plus 4, 6. How many hydrogens do I have now?
4,
4. 2 times 2, or 2 times 1 plus 2. That's going to be 4 hydrogens. Now, on the other side, I'm going to balance my next easiest element. Well, that would be sulfur, right? But sulfur's already balanced. So then I go to the next easiest one, which is hydrogen. So hydrogen has 4 on this side, 2 on this side. What do I do? Put the 2 in front of H2O, right? And that's going to multiply the 2 times 2, give me 4. And the 2 times 1 oxygen plus 4 gives me 6. So you'll notice that if you balance the easiest elements first, the hard ones balance themselves. If you balance the easiest elements first, the hard ones balance themselves. Now there are some ridiculously hard to balance equations that I'm aware of that I could throw at you, but you're not going to get those in class, so I don't want to be mean and do that. But there's also a mathematical way to solve these with certainty. It is also kind of interesting, and yeah. So I'm going to show you that way just for giggles, I guess, because if you really do have a challenging equation, it may be easier to balance it that way. But usually that method, unless you're really good at math, takes longer. Okay. But we understand this way? Okay. This is probably going to be the easiest way. It's probably going to be the way you want to use. Well, let's say you have something ridiculous. Let's say you have something like, oh, I don't know. C6H12O3 plus O2 goes to form CO2 and H2O. Okay. Now, something like this, you could balance it the way that I showed you, but it would be challenging. However, You could also balance it in a mathematical way. And the mathematical way works like this. First of all, you put a variable in front of each exponent. Each variable represents an exponent, or rather a coefficient. So I could say that this is, I'll call this A, B, C, and D. Okay? These are my coefficients. And what I do is I make an equation for each element. Okay? So for carbon, I have 6 carbons for every A, so I'd say 6A, and there's no carbon here, so 6A is equal to C. There's no other source of carbon, right? And this is only one C here, so 1 times C. So 6A is equal to C. Then for hydrogen, for hydrogen, 12 times A is equal to 2 times D. And that's all the hydrogen there is, right? Now for the most complicated of the equations, oxygen. So for oxygen, I have 3A plus 2B is equal to 2C plus 1D. Okay. All right. So what I do here is I have to use this as a system of equations. I know that C is equal to 6A. If I divide both sides by 2 here, I get D is equal to 6A. So 6A is equal to D and 6A is equal to C, so that means 6A is equal to both D and C, right? And if that's the case, what I can do is I can solve for B in terms of A, just like I've solved for D in terms of A and C in terms of A. So if I solve for B in terms of A, what I'll do is I'll substitute this for 6A. So I'll say I have 2 times C, which is the same as 6A, plus D, which is the same as 6A, 2B plus 3A. And then I'll get 12A plus 6A is equal to 3A plus 2B, which of course that gives you 18A is equal to 3A plus 2B. Oops. And then I subtract 3 from both sides, and 2B is equal to 15A, which means that B is equal to 7.5. No, 7.5, yeah, 7.5 A. So now I have each of these solved in terms of A. And at this point what I do is I just establish one of these as a 1. And so I'm going to establish the one that is probably worth the least. A seems to be worth the least because it takes 6A to make a C, 6A to make a D, 7.5A to make a B. A is worth the least. So I'll put that as a 1. And if I put that as a 1, then I substitute 6 times 1 is 6, right? 6 times 1 is 6. 7.5 times 1 is 7.5. Now, of course, you cannot have a balanced equation with a half amount, right? So what do I need to do?
Scale it up.
Scale it up, double everything, right? So this becomes a 2, this becomes 15, this becomes 12, and this becomes 12. And that is how you balance it mathematically. No question. Should I have bothered showing you that?
It's pretty neat.
It is pretty interesting. It's really effective for very complex equations. But for simpler equations, it's not worth the time. Yes?
So what type of reaction would this be? Would this be a hydrocarbon?
Yes, so this would be combustion. And typically anytime you burn hydrocarbon with oxygen, and the giveaway is also the CO2 and H2O. That's not a guarantee because you can also have other things that produce CO2 and H2O. But yes, this is a combustion reaction.
And then one more question, the sodium hydroxide and hydrogen sulfate reaction which kind of reaction was that?
That is a double replacement. 2 compounds switch ions to form 2 new compounds. Because the hydrogen in that reaction switched place with the sodium.
So are there equations that cannot be balanced?
No, you can always balance an equation. If the equation cannot be balanced, that's probably it's an example of a improper equation, in the sense of you're predicting something as a product or something as a reactant, which would not be able to come from that. Because balancing equations is essentially about basically demonstrating the law of conservation of mass. The law of conservation of mass, matter cannot be created or destroyed, except through nuclear reactions. So in a chemical reaction, matter is not created or destroyed, which means that the number of atoms on the reactant side has to always equal the number of atoms on the product side. They can't change identity and they can't change number. So you must always be able to balance the reaction. If you come across one that you cannot balance, bring it to me and I'll be able to show you where the mistake is.
Because in lab, we had to mix, I think it was copper nitrate and hydrochloric acid or something, and then we had to predict like what the products were, and so I guess, and then we tried to predict the products and we couldn't balance it, so I guess we chose the wrong products.
Probably, yeah, and that's definitely possible. The reaction I think you're thinking of might be copper and nitric acid.
Oh yeah, that was it.
Yeah, that one is a tricky one. I can actually go through that one with you and show you how to balance that using the other method, not this method. Okay, so I believe, if I recall correctly, that's Cu and HNO3, right? And it goes to form copper 2 nitrate. Nitrogen, was it a brown gas?
Yeah, it was.
Okay, nitrogen dioxide then, and H2O. Okay. Because nitrogen dioxide is brown. Nitrogen monoxide is laughing gas. And I assume you weren't laughing in the lab, so. Alright, so now here's the deal. This is a complicated reaction. But if you do like I mentioned before and you list out your elements, you can do this fairly easily. Somewhat easily. So copper, hydrogen, nitrogen, and oxygen. This thing is almost up. Okay. So So how many coppers on this side?
One.
One. How many hydrogens are there?
One.
One. Nitrogens?
One.
And oxygens?
3.
There you go. How many coppers on this side?
1.
Hydrogens?
2.
2. Nitrogens?
4. 3.
3. Oxygens?
9.
9. So, if we're looking at this, copper appears in how many compounds?
1. Oh, 2.
2. Hydrogen appears in how many compounds?
2.
2. Nitrogen appears in how many compounds?
3.
3. And oxygen appears in how many compounds?
4.
4. So copper and hydrogen are going to be the easiest ones to balance, so we'll start with those. So copper is 1, copper 1, balanced. Hydrogen 2, hydrogen 1. What do I do?
Put a 2 in front of each number 3.
Yeah, and 2 in front of each and 3. And that is going to change my numbers a bit. I'll now have 2 hydrogens, right? And 2 nitrogens, and 6 oxygens. So now I go to nitrogen here. Now whenever you have an odd number that you're trying to balance with an even number, what do we do?
Make the odd even.
Double the odd to make it even. Now, which compound is causing the number of nitrogens to be odd?
Oxygen. Oh, wait. Hydrogen?
Which compound?
The
This one or this one?
second one.
The second one. There's only one nitrogen here. So that's the one causing nitrogen to be odd. You don't have to double everything. You just have to double the one that's causing it to be odd, which in this case is the NO2. So I'll double this, and that will give me how many nitrogens now on this side?
6.
No.
Oh,
4.
4. Yeah, we didn't double the whole thing, we just doubled this. So now is 2 plus 2, that's 4. Now I also increased the number of oxygens, right? So this is how many oxygens now?
9. Wait. 4. 6. 10. 11.
11. 6. And if you have to, write it out. I have 6 here, 2 times 2, 4 here, and 1 here. So 6, 4, and 1. That gives me a total of 11 oxygens. Alright, so now I have doubled my odd to make it even, and I will now balance the nitrogens. I have 4 here, 2 here, what do I need to do?
Change that 2 to a 4.
Change the 2 to a 4. Or if you like to think of it this way, you could also multiply that coefficient by 2. This is the coefficient was 2. 2 times 2 is 4. And that changes everything, almost. And now I have 4 hydrogens, 4 nitrogens, and how many oxygens?
12.
12. Now at this point, what do I want to balance next?
Hydrogens.
Hydrogen. If I unbalance one of my easier elements, I always go back to rebalance that before I go to a hard one. Okay? So I have 4 hydrogens here, 2 hydrogens here. What do I have to do?
Water, double it.
Double the water. We'll put a 2 in front of this, multiply it. 2 times 2 is 4 hydrogens.
12.
And now how many oxygens do I have?
12.
12. And so conveniently, oxygen just balanced itself. So now I want to look at predicting the products. We have a little bit of time left. So let's look at the reaction practice one. It only gives you the reactants. I want to predict what type of reaction we have, and then I'll show you how we predict the products for each one. So, what type of reaction is question 1?
Synthesis.
Synthesis. How can you tell?
One of each.
Yeah, it's two elements, right? It's just two elements, so that's the synthesis. You can put a S for that. Now, what about the second one? What would that be?
Decomp?
Decomposition, because all it says is aluminum sulfide, right? And if it's just aluminum sulfide, that's one reactant, that would have to be decomposition. What about number 3?
Single replacement?
Single replacement. You have an element, iron, and you have water. Let's go ahead and do let's do that one for practice. So it says you have iron 3. Now when it says this iron 3, it means that when it forms the compound, it'll have a +3 charge. But of course, iron as an element has no charge, right? It's just going to be by itself. Now, water is H2O. Okay. So now in this case, this can be a little bit tricky because you could also write this as HOH. And technically water does sometimes switch out one hydrogen and give you hydroxide as the minus ion, or sometimes water will switch out both hydrogens and give you oxide as the minus ion. In this case, it will do the first. So we know, whenever we are predicting products for something like this, you want to identify the charges first. We know that iron is going to form a +3 charge in this case because it says iron 3. It otherwise is a transition metal and you would not be able to predict it. Okay. Now, hydrogen has what charge?
+1.
+1. Oxygen has what charge?
-2.
-2. So if the iron and the hydrogen switch places, because remember, like replaces like, so that means these guys are going to switch places. Which means iron is going to go with what?
Oxygen.
Oxygen. And if iron goes with oxygen, iron being a +3 and oxygen being a -2, what's that going to give you?
Fe2O3.
Exactly. Fe2O3. The lowest common multiple of 3 and 2 is 6. I need 2 irons to give me a charge of 6, and I need 3 oxygens to give me a negative charge of 6. So that will balance the charges. What's going to be left?
H2.
H2. Hydrogen, remember, is a Brinkelhoff element, so it's not going to be H, it's going to be H2. Now once you have this set up like this, now you can balance it, right? And so once you get into the habit of balancing it element by element, you are not always going to need to have to list out your elements. For example, in this case, I could say, okay, well I see I have 2 irons here and 1 iron here, so what am I going to do?
Just follow the single element.
Yeah, I'll put a 2 in front of iron. And then I say, okay, well I have 3 oxygens here, and I have 1 here, so I'm going to put a 3 in front of the water, right? And then I have 6 hydrogens here and 2 here, so I put a 3 in front of the hydrogen. 3 times 2 is 6. And then if I check each of those, you'll see that it's balanced. Now, in the early stages, you may want to list out your elements and get a lot of practice like that, so that when the test time comes around, you're going to be so well versed with this, you won't even need to list out your elements. But practice, I recommend listing them out, because that will make it easier for you when you need to be a little bit more speedy later on. Okay, so now let's take a look at the next one. Ooh, actually, let's do a mean one. Let's do number 5. I like that. Okay, number 5, it says hydrogen sulfate and aluminum hydroxide. First of all, what type of reaction is number 4?
Double replacement?
Double replacement. How can you tell?
There's 2 different polyatomic ions, and they have.
Well, there's two different. There's one polyatomic ion, but there is two ionic compounds, right? Anytime you have two ionic compounds and an ionic compound and an acid, you can count on it being a double replacement reaction. So number 5 would be a, what do you think? What kind of reaction would number 5 be? How about you, what do you think? Double replacement, yeah. Another acid and another acid and ionic compound. So very good, very good. So that'll be double replacement. So let's do this double replacement reaction. These are some of the most challenging to predict the products to, which is why I wanted to do it. So what is hydrogen sulfate? What's the formula for hydrogen sulfate?
H3SO4.
H2SO4.
Just kidding.
Did you say something else?
No?
Okay, H2SO4.
Yeah.
Okay. So hydrogen is a +1, sulfate's a -2, so it's H2SO4. What about aluminum hydroxide? What's the charge of aluminum?
1.
Nope.
+3.
+3. And what's the charge of hydroxide?
-1.
-1. So what's the formula for aluminum hydroxide?
ALOH3.
ALOH3. It always makes it so much easier, especially when you're predicting products, to go ahead and write out the charges of your ions. So hydrogen, as we know, is a +1, sulfate's a -2. Now that we know our charges, we can predict our products. So when I switch these ions, like replaces like, what's hydrogen going to go with?
The OH should make it water.
Yeah, it's going to go with the OH. So hydrogen's a +1 and OH is a -1, so that gives me HOH, right? Now why don't I include this too? Why don't I put H2OH3, excuse me. Because you have to remember that when these separate, this doesn't separate into OH3, this separates into, because remember these are dissolved in water, this is going to separate into an Al3 plus ion and 3 separate OH minus ions. Likewise, H2SO4, it doesn't separate into H2 ions, it separates into 2 separate H plus ions and an SO4 2 minus ion. So keep that in mind, that even though they look like they're together here, when they're dissolved in a solution, they're actually all separate ions. So when you put them back together, you don't keep these together, you don't necessarily keep the subscripts here. You put them back together based on their charge. And so OH is a -1, H is a +1, you just need one of each. So it's HOH, or, as we like to call it, water, H2O. Now, what's the other compound that would form?
ALSO4. Oh,
Not quite.
Al2SO43.
Al2SO4 When you put it back together, you have to put it back together according to the charges. And since aluminum is a +3 and sulfate is a -2, once again, that lowest common multiple is 6, right? So I need 2 aluminums and 3 sulfates. Now, here's where it gets fun. You have to balance this. So, don't worry about balancing it when you're predicting the products. When you're predicting the products, focus only on the ions. Focus only on the charges of the ions. Okay? But once you've correctly predicted the products and put them back together according to their charges, now you can balance it. Now you can balance it. And for this one, I am going to list out my elements because this is a little bit trickier. I have H, S, O, and Al. H, S, O, and Al. So how many hydrogens do I have on this side?
5.
5. How many sulfurs do I have on this side?
1.
How many oxygens?
7.
And how many aluminums?
1.
How many H's do I have on this side?
2.
How many sulfurs do I have on this side?
3,
How many oxygens do I have on this side?
13,
13. Because there's 12 here, 3 times 4 is 12, and 1 here. And how many aluminums do I have?
2.
Alright. So, like I said, like I mentioned before, list them in the same order, it'll help you keep track of them better. Now, let's identify which one would be easiest to balance. What are the easiest elements to balance here?
Hydrogen, aluminum,
Aluminum? Yeah, aluminum only appears in 2 substances, right? Here and here. That's gonna be pretty easy. What else? You mentioned one?
hydrogen,
Hydrogen's not as easy. You mentioned
Sulfur.
sulfur.
that was
So
it.
sulfur will be a little easier because sulfur is only present twice, in 2 compounds. What about hydrogen? How many compounds does that appear in?
3,
3. 1, 2, 3. So that's going to be a little bit harder, and then oxygen appears in
4,
every single one. So we're going to hold off on hydrogen and oxygen till the end. Let's focus on aluminum and sulfur. Okay. So we can do sulfur first. That's fine. I have 3 sulfurs here, and I have 1 over here. So what do? Yeah, multiply by 3, right? But that's going to multiply everything. So 3 times 2 hydrogens is
6.
6 plus 3, 9. Now how many sulfurs I have? Just 3, that's an easy one. But then how many oxygens now?
12.
Plus?
13. Oh. 15. I mean,
15. 15. 12 plus 3, so that's 15, very good. Now that I've balanced that, because remember, whenever I put a coefficient here, I have to figure out how much of each I have again. Alright, so now go to the next easiest element, which is aluminum. I have 2 here, 1 here, what do?
put a 2 in front of the H2.
Yeah, multiply the aluminum by 2. And that's going to, once again, distribute to each one of these. And the subscripts outside of parentheses multiply the inside, but the coefficients also multiply. So that means I have how many oxygens in this little group? 2 times 1 times 3. 6, right? And then I have how many oxygens here? 12. So 6 plus 12?
18.
I have 18. How many hydrogens do I have on this side now?
12.
12. 2 times 1 times 3 is 6, plus 3 times 2 is 6, so 6 plus 6 is 12 hydrogens. And I also have 2 aluminums. Alright, so now aluminum is balanced. Sulfur is balanced. I'm going to go with the next easiest one, hydrogen. I have 12 on the left side, 2 on the product side. What do I have to do?
Multiply water by 6.
Water by 6. That gives me 6 times 2 or 12 hydrogens, and 6 times 1, 6 oxygens, plus,
12 oxygen, so that'll be another 18.
yep, and oxygen balanced itself. So this one was a little intense, wasn't it? But if you balance the easier elements first, the hard ones will balance themselves. There's, of course, obviously a lot more practice here. As you'll notice, number 6 is what type of reaction?
Combustion.
Combustion. So the products there are just going to be an obvious CO2 and H2O. And then you can balance that. The answer key to each one of these is posted on the website, both under the workshops and under the practice problems. So if you go to the events and workshops, scroll down to where this workshop is listed, and it'll have the answer keys to each of these. And you can, if you wish, work out some more of these in practice. This will become especially important when you get into solution stoichiometry and net ionic equations. Have you gotten there yet?
No, ionic.
Net ionic, you just got there? Yeah, so net ionic equations, this will be very helpful to you in predicting the products of the cymatic equations, and then also in recognizing how to break these up into ions. All right, excellent. Well, thank you very much for coming.
Thank you.
Thank you very much.